where we left off for assignments. Now that you guys know how WebAssign works, it's the deal. So it's awful on one level. On another level, guess what? You're going to be one step ahead of everybody else next year when you actually go and take your undergrad classes. So this is standard now for your entry-level classes.
That's what I thought. Yeah. There's just so many ways to type the same answer. Like you could do K, you could do E.
Yeah, that's why I want to actually remove any algebraic and just have it be only do problems that require a strict numeric answer.
Can you make sure they're clean numbers? Or can you like work on making them cleaner numbers?
Probably not. I mean, I could actually. All right, so let's focus on this first. Okay, so let's suppose you're at x away, and notice that it's symmetrical. In other words, this is along an axis. Okay, this is the ring still. And so I just want to go through the derivation. The electric field, right, due to some element of charge. Notice every single bit of charge is equidistant from the point that you're evaluating at. All right, this is important because when you actually go to evaluate the integral, so you have the integral of dq over script r squared. And remember, it's going to be the cosine component of this guy's going to exert a force in this direction. This is E script r. So then E little r, or you could say Ex, because it's in the x direction, is going to be equal to the cosine component. Yes?
Everything's the same distance from all points around the...
Correct. Each of these pieces are all the same distance script r away. And script r squared is equal to big R squared plus x squared. And so dq, this is a ring is basically just a line of charge. And so dq dl is equal to the linear charge density, lambda. So I'll zoom in a little bit. Okay? And so therefore dq equals lambda dl. And dl is what? The infinitesimal length along the circumference. So dl is going to be simply r d theta. And you integrate it over all theta, which means theta goes from where to where? 0 to 2 pi. And what you end up with is that the total charge, Q, is going to be lambda times 2 pi r. This makes sense. This specific problem, yeah. And the reason is because everything else came out of the integral. Why did it come out of the integral? Because it's constant. It's equidistant. Every point along the ring is equidistant from the point with which you're evaluating it at. So this is equal to cosine of phi is going to be x over script r times 1 over r squared integral dq. And there you have it. And so what we end up with is that the electric field at x is x over r cubed times this factor, lambda times 2 pi r. And so, and of course, what am I missing? What am I missing throughout the whole entire thing? Yeah, 1 over 4 pi epsilon naught. And this, I'll always do this.
Can we define it as K?
No.
Just flip.
You'll see why. Because, and then this becomes over 4 pi epsilon naught. So, yes, shoot.
So with the integral on the way right,
Yeah.
you replace that with lambda r d theta.
Correct, and then integrate.
Integral from 0 to pi.
Correct. Now notice, what happened if lambda depended on theta? What does that mean?
Then it would stay.
First, what does it mean for lambda to depend on theta? We're just assuming it's uniformly charged.
Oh, that would be like if you have like a conducting ring.
Not a conducting ring.
What if it was like 4 of them?
It would be if, for some reason, you'd need an insulating ring. For reasons that are not obvious right now. It would have to be an insulator. And you'd construct it in such a way that charge increased, let's say, or you could say you can imagine charge being sinusoidal, like where it's maximized here and minimized here. Notice, and it's continuous throughout, notice lambda would be dependent on what? Theta. But for right now, we're only going to deal with linear charges, uniform charges, yes.
Is linear charge density, is that like a value that's given to us, or do we have to find that, or how does that come into play?
Usually, it's something you can express it in terms, like it's usually things are expressed in terms of the linear charge density. Sometimes it'll be given to you. By and large, it's something that you're going to get acquainted with. It's kind of like distribution of mass. Sometimes it'll be given to you. If it is given to you, usually it's given as a function, and then you have to integrate that function. But you'll see yeah, when you get an actual problem, that's when you'll actually see how different situations. Yes.
2 questions. Where did the lambda r d theta, and then where'd you get the lambda?
Because DL corresponds to this arc length, right?
Oh, so it's r d theta. Okay.
And that arc length has a measure of r d theta.
And then where did the 2 pi r from?
I just integrated over d theta. Because it's a ring, so you're integrating over the whole entire ring. So now we have this expression. What do we have to do? And this is a very good exercise. We have an expression. We have to find limiting cases. Meaning we have to actually assess the validity of this thing from a physical perspective. So let's actually look. Maybe I'll zoom in a bit more. Okay, we have EX is equal to X times, I'm going to write everything out, lambda times 2 pi r over 4 pi epsilon 0 x squared plus r squared to the 3/2. That's this.
Oh, you placed the R.
So now, if we get really close in,
It's not like the 2s and the 4s.
you'll see. There's a rhyme. There's a reason for this. So if you get really close, what do you expect the electric field to be? 0. Why?
It's equal force on all.
Yeah, equal force on all sides. Does that agree with that? Yes or no?
X is 0. Well, yeah. It's X is
If you put x equals 0, and you get 0 times some other number, whatever that number's. So that's reasonable. What do you expect this thing to look like from very far away? Be careful. What should that look like? Meaning a point charge. And what is the electric field from a point charge? What's value is it? KQ over r squared, or Q over 4 pi epsilon naught r squared. Let's show that. So let's see what this means. So to show this, what does that mean? That means x is significantly greater than r, right? So what I'm going to do is I'm going to factor out what? let's see. I'm going to factor out. So here you have lambda x times 2 pi r, right? And then you have the 4 pi epsilon naught, right? And what I'm going to do is factor out. So this is going to be x squared times 1 plus r over x squared, and all that's 3/2. Is that correct? So now, this is equal to lambda times x times 2 pi r over 4 pi epsilon naught, right? And now what's x squared raised to the 3/2? X to the third, right? And then we have a 1 plus r over x squared, and that's to the 3/2, correct? Now what's lambda? Which is? Q over L. What's L? 2 pi r. So we have that EX is equal to Q over 2 pi r times x times 2 pi r over 4 pi epsilon 0 x cubed times 1 plus r over x to the 3/2. Now what happens? Now we cancel. Boom, 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 squared. So we get Q over 4 pi epsilon 0 x squared times this factor. But what's r over x approximately? That's right. So therefore, the electric field is approximately? That's right, epsilon 0 x squared. And remember, x squared is what? It's effectively your r squared, because this distance, the distance from the center of the ring, right? This distance to the top of the ring is effectively equal to this distance to the center.
That's not it, is it?
Oh, I mean, just take a look.
Oh, right.
I mean, we can actually experiment with this to see precisely how close they are. Yes.
What's that thing that you always did last year? It's like sine of x over x.
Yeah, that approach is 1. You'll see me do that this year too. So that is your first exposure to what are called limiting cases. And you're going to have to get good at this, because limiting cases is really how you test the reasonability of an answer.
It's like looking at the two extremes.
Correct. And it should correspond to physically like what you think it should physically observe. Because it's not obvious when you go to continuous distributions that this thing, you don't know if, like looking at this, did anybody here know this was right? No. So the only way you know it's right if it corresponds to something that you would expect in a much simpler case. So now we go to a line. The line is a harder problem. That's right. That's right. So we take a line. We take a line of charge. I'll throw this up at 200. Okay, here's the line. And we're going to do the same exact procedure. I'm going to find the electric field at some symmetric point above the line. So let's say right there. Not in this class. Generally, no. I mean, it just gets ugly. It's not that hard, though. It's not that hard.
Yeah.
Just tedious, probably.
Actually, this should technically work for non-symmetric case. There's a reason why you start off with the symmetric case. So now, let's construct our coordinate system. This thing has a length of what? Let's say it has a length of 2L.
Oh, I know this.
Right, so you read this.
The one thing I got right from the exam.
Okay, so
The one thing he taught me was on and I was really happy.
So now, let's construct our coordinate system. Let's set the origin here. So this point's going to be L, and that point's going to be negative L. Now what?
Right now, that's in
Correct. Let's say this is some distance r away, little r. Hmm?
He's like screaming.
So now,
He's just teaching.
that is how he rolls. So now,
I would like to say I'm happy that you don't talk that loud.
no, it's trust me, it's its own entertaining thing. So now what? Take an infinitesimal chain, right? Or take like a little bit of line charge. Which side do you want first? Let's suppose this is a positive. Let's suppose this is a uniformly positive line charge. So you want it on the positive side? Sure. So you take this piece, right? And where's this piece located? It's located x away. Okay? What is the length of this piece? Dx. Right? And so what do you have here? You have that the uniform, let's suppose it's uniform charge density, meaning lambda is constant, and lambda is always equal to dq dx. Now, so this right here is your dq, has length dx. Now, what is the electric field at that point from that element?
Lambda dx.
Where is it pointed?
Points right.
So that's right. It's this is where dE script r is pointing. Notice if I take a symmetrical point on the other side, where's that going to point? So therefore, what component survives? The y component, which is why you take the symmetrical case first. So the only component that's going to survive is dE little r. And so now we set up our coordinate system more specifically. We'll call this phi. And so we have dE little r is equal to dE script r times the cosine of phi. Same deal. Now I'll zoom out a little bit to 150. All right, so dE little r is equal to what? Well, what's dE script r equal to? One over 4 pi epsilon naught times lambda dx. Well, let's just leave it as script r squared. You don't know which form you're going to put this in, because that's just dq. dq equals lambda dx. Okay, so now what we have is the following. We have 1 over 4 pi epsilon naught, and then we have lambda dx over r squared times the cosine of phi. And so your first gut is to do what? Find r squared in terms of x and little r, right? That's your first gut feeling. And then find cosine phi in terms of what? X, or, yeah, it would be what? R over script r, right? That's what your gut's telling you to do. Don't do it. Don't do it. You'll do it, but I'll tell you, you'll end up going nowhere. So this is the first time you're going to see integration by substitution. And what we're going to do is we're going to do something called trig substitution. So the way you do this is like this. Which parameter is actually a constant here? No. Which parameter? X, little r, or script r? Little r is a constant. So the way you do trig integration is you say, okay, I need to exploit that constant. So you say, all right, the tangent of phi is equal to what? X over little r. Right? So now you have a relationship, a direct relationship between x and phi that is not linked to another variable. In other words, x and phi are linked by a constant and a function. What can you do now? You can differentiate this. In other words, we have x is equal to r tan phi, so dx d theta is equal to what? Little r is a constant. That comes out, so now we just need to know what the derivative of tangent theta is. What is it? Be careful. Very good. It's secant squared. Or this is equal to r over r times secant squared. But secant squared is simply 1 over cosine squared. And so now what we have is a relationship we can plug in for dx. So we have dx, sorry, that should be a phi. Dx is equal to r d phi over cosine squared phi. Right? So now I'm going to zoom out a little bit more. Now, I want to know, I want to express this r squared, that script r squared in terms of phi. How am I going to do it? Yet again, what do I want to do it in terms of? Using little r. So, we say that the cosine of phi is equal to what? Little r over script r. Right? So therefore, 1 over script r is equal to cosine of phi over little r. Which means 1 over script r squared is cosine squared phi over little r squared. Are we ready?
Are you about to do something?
Yeah, now I'm about to sub everything in. So we get ER, it's technically DER. I need to, let me actually lasso this just so I can squeeze a D. Oh, there you go.
Wait, so you're going to put that, you're going to sub in cosine.
I'm going to sub in everything. So DER is 1 over 4 pi epsilon naught, and then we have that times that lambda. And then we have dx cosine phi over script r squared. Right? I just rewrote it. So now, this is equal to lambda over 4 pi epsilon 0. Okay? Dx is r d phi over cosine squared phi times cosine phi, right? And then times 1 over r squared. But what's 1 over r squared? Cosine squared phi over little r squared. Pretty sick, right?
I completely got lost in that. I'm sorry.
Where are you lost? The last part.
But then, like,
All right. See how you have a 1 over r squared here?
yeah.
Let's multiply that by, let's find out what 1 over little r squared is. We found that out earlier. That's right. So you multiply it. Yeah, I'm just subbing in for that 1 over script r squared.
Oh.
So each of these terms, this is this thing, this is this, and 1 over r squared is that term.
So it's just. Okay.
And so you get massive cancellation. Let's take a look. This cancels with this cancels with this, and now we have lambda over 4 pi epsilon 0 r times the integral of cosine phi d phi. But what's the integral of cosine? Sine, that's right. What, is it sine or a negative sign? It's negative sign. Is it? Wait. Let's think this through.
No, it's just sine.
It's just sine.
Wait, why is lambda constant?
Lambda's I told you it's a linear, it's a uniform charge density. Doesn't have to be. It could be a function of x, in which case all bets are off.
Why did the r? Oh, because the little r is a constant.
Little r is a constant.
It's an r squared and an r on top, so you left with that one r. Is this thing infinite with an r?
It's finite. So now what we end up with is that this is equal to, this is ER, and this is equal to lambda over 4 pi epsilon 0, and then sine of theta, or sorry, sine of phi. Now what do? Now we need to evaluate it, right? But wait a second, do you really want to evaluate it in terms of phi?
Why is that 2 pi?
Yeah, why is it 2 pi?
That's 4 pi.
Oh, it's a funky 4.
Yeah, I originally wrote 2. Okay? You'll see why I accidentally wrote 2 shortly. So now, do you really want to do things in terms of phi? The limits of integration? And the answer is no. And the question is why? What do you really see this whole problem in terms of? Like if we go back to the original problem, right? What are you actually integrating over? The length. So in other words, we want to get this back into which form? L, that's right. Because we know that the limits of integration go from where to where? From negative L to L. That's right. So I'll just go and put this back into that form. So you get lambda over 4 pi epsilon naught little r. And what's sine of phi? X over script r, meaning x over the square root of r squared plus x squared. And there you have it. And now we evaluate this from where to where? Negative L to L. This is why, like, the summer assignment, I think for some people, so this is E of little r is equal to this. So you get lambda over 4 pi epsilon 0 little r. And now it's going to be L over the square root of r squared plus L squared minus negative L over the square root of r squared plus negative L squared. Right? So now, what happens here? That negative L becomes positive by the nature of it being squared. And then this minus that becomes positive. So they share the common denominator. They have the same denominator, and you have L plus L. Or in other words, ER is equal to lambda over 4 pi epsilon naught R times 2L over the square root of R squared plus L squared. Is it right? That's right. We have to do limiting cases. So we get 2 lambda over 2 pi epsilon naught. Get my head out of there. Lambda over 2 pi epsilon 0 R times L over the square root of R squared plus L squared. So there's our solution. So the first question is, what happens when, what is the one that we know?
When L is significantly smaller than R.
Meaning that when you're very, very, very far away. All right. So in order to actually do that, we're going to go back here. We're going to return back to this. Because in order to actually assess that case, I need to either teach you what a linear approximation is or the binomial approximation. Both of them are basically the same in terms of difficulty. I think I'll do the linear approximation. So if you have some function, here's f, here's x. Right? And I want to know, let's suppose you have some point x0. And I want to find the value of this function, an approximation for the value of this function, at some point around x0. What can I do? If I want to find approximately the value of this function at some point around x0, what can I do? That's right. In other words, I take a tangent line at x0, right?
What is this called?
Whatever. Well, there's Taylor's theorem, which is an infinite sum.
It's like the using triangles.
You'll see. So, as you can see, here's x0. And this isn't a very good. No, I don't want it like this. I want to have some type of exponential character. So there's x0. If I wanted to find f of x at that point, what I could do is I could draw a line tangent line, right? And notice, at that point x, at this point x, how close is my approximation? That's right. So in other words, it's just this distance. That right there. No. It's not Euler's method. This is just a linear approximation to a function. Right? This right here is the error. So let's take a look. Well, it's not that's different. You're thinking of something else that's different. All right. So right here, if I were to ask you, how do I find this? Well, the fact that this is tangent means what? This is tangent at x0. What does that line define? Slope of that line is? What's the slope of that line? F prime at x0. Right? And what is f prime x0? Well, it's approximately equal to f at x minus f at x0 over x0. So therefore, we can use this to find our approximate f of x. We rearrange, we get f of x is equal to what? F prime at x0 times x minus x0 plus f of x0. And that's a linear approximation to f of x. And that makes sense, right? I mean, basically, all we're doing is taking the slope at the tangent line and putting that into point slope form. And we're saying that f of x can be approximated linearly by that. So generally speaking, what x0 are we generally going to be looking at? 0. We're generally going to be looking at where x0 equals 0. So it even becomes simpler that in general, if x0 equals 0, then f of x is approximately equal to f at 0 plus f prime at 0 times x. So now what do? We go back to the other problem. That's not the other problem. That's not it. Wait, is that it? Yeah. Wait, is that it? All right, sweet. So now, we have ER. We want to find ER for what point? Where R is much greater than L. And notice, what does that mean? What does that physically mean? Let's see. Aman, what do you think that physically means? What do you think this physically means? Finding the electric field at a point where R is much, much greater than R. Yes. Do you remember what little r referred to? Little r is the distance. Here's your line, little r is the distance away from that line. Okay, and so then what would this look like? Very far away. Point charge, right? So what is that? What should that look like? KQ over, in this case, little r squared. KQ over r squared. So we should always be seeing this. So let's take a look. So we have lambda over 2 pi epsilon 0 r. And then what do? This is times L. What do I factor out? Focus, Zach. Factor out the square root of r squared, which would be an r times the square root of 1 plus L over r squared. I just went and jumped ahead. And so now what do we have? Actually, I don't even think we need to do anything else. I think we're good. I think we're real good. Yeah, we're done.
Wait, isn't the side on the right?
Hold on to it. We're going to need it at some point. Yes.
Isn't the side on the right going to get super close to 0 again?
Let's see. Oh, you might. Wait, no. No, you'll see. Because watch, what is lambda equal to?
DQ over
No.
Q over L.
Q over the length. But what's the length?
Like, almost.
What is the length?
Well, it's infinitely small.
2L. So lambda is uniform charge density. So it's the charge Q over the length, which is 2L. So you have Q, and then you have 2 pi epsilon 0 r, and this is Q over 2L. Actually, that's an r squared because those two factored, or those two, that one over there. Notice what happens. L's cancel. And so what are we left with? This is equal to Q over 4 pi epsilon 0 little r squared times the square root of 1 plus L over R squared. And what is L over R approach? It's close to 0. So is this correct? Nice. So now what happens when you get up on the grill of this thing? Now we want to go and look at the other end. On the other end, we have ER for R much, much less than now. I think this is where I need it. And what did it equal? It's lambda over 2 pi epsilon 0. There's an L in the numerator. There's an R in the denominator. And then there's what? R squared plus L squared. Check that this is right. First, that this is the correct electric field, right?
Wait, so Mr. Khalil, there's like a certain point where making it longer is not gonna affect the electron or proton anymore?
Effectively, yeah. It's effectively infinite relative to that infinitely long. Yes. So let's actually see this. Was this the previous electric field? All right. So now this is where it gets a little tricky. I'm not sure if, no, this is right. So now what do I do here? I factor out a square root of. Oh yeah, I would factor out the L squared from here. And you get lambda times L over 2 pi epsilon 0. And then you have an R. And then it's going to be L squared times R squared over L squared plus 1. Is that right? And so this is equal to lambda over 2 pi epsilon 0 R. And then L, square root of L squared becomes the L. And then you have the square root of 1 plus R over L squared. And what happens? The L's cancel out. And then what happens in the limit? This goes to 0. That goes to 1. So this becomes approximately. This goes to 0. R over L quantity squared. 1 plus that goes to 1. The square root of that goes to 1. And so what are we left with? Lambda over 2 pi epsilon 0 R.
So if you know lambda, you can find out like the max electric field line you produce.
1 second. So now notice, when you get up close on this line of charge, how does the electric field behave? Does it behave as a 1 over R squared? It behaves like a 1 over R. So if you have a point, you get up close to a point, it behaves like 1 over R squared. You have a line, you get up close to the line, it behaves as 1 over R. What happens if you have a plane and you get up close to a plane? Think about it. Point, right, has how many dimensions? 0. A point has 0 dimensions. Right? You get up close to it, or anywhere from it, it's 1 over R squared. A line has 1 dimension. You get up close to it, and 1 over R. Take a plane, how many dimensions? 2 dimensions. You get up close to it, it would be 1 over R to the 0. What's R to the 0? 1, which would mean the electric field should behave like it's uniform.
It doesn't matter how far away you are.
Right? Notice you have a volume.
Oh, it's the whole thing. Everything's
If you have a volume, right? You go interior to the volume. How do you think the electric field's going to behave? It's going to be R to the first, linear. Remember this from last year? So let's go.
just when you go inside the earth, it's switching.
That's right. It becomes linear. The gravitational field linearly increases all the way till you reach the surface, and then it decreases 1 over r squared. Sure. Where to?
Where you have the result of r much greater than
Okay, that's this. If I'm going too fast, just tell me. Seriously. All right. What'd you say? Just wait till the next one. Next one. Next one, and then you guys can actually start hitting up some problems.
Like, I don't know how this is applied, so I'm like, I have a bunch of like.
Well, you have to derive some of these.
Yeah, I get that. But like, it
So
doesn't make sense until I get something.
take out your free response questions. Take out your free response questions. So now take a look at something like. All right. So go to, let's say, number, I think 4. 3, 4. Okay. So 4, notice 4 requires what? No, well, it does require. It requires Gauss's law, which we're not there yet. Gauss's law is going to simplify a lot of this.
Hopefully.
No, definitely.
I hope that.
But if you go, let's say, to number 6, right? What do you see? It's a quarter of a circle, exactly.
Yeah, I saw it. It's not in the package, right?
No, it should be. It was first day stuff.
Yeah, I know I got it. I don't know.
I may have another one. So let's do the disk, and then after the disk, I want to give you guys some time to work on this. Because after the disk, I only have one more example, which is sphere. And this one I'm going to do, I'm going to do the hollow sphere, which is the harder one. Because you can generalize the solid sphere from the hollow sphere. All right, I have another set. Zach, just wait. It's in the back.
I'll just click on the view.
All right. So now, let's go to the disk. I'm still unsure of how I feel about the software. I think it has
Yeah, it's definitely
what in terms of the software. Like you think that it's much smoother?
Yeah, it's a lot smoother than last year. 'Cause
Yeah.
last year you were like milling around with like shapes and stuff.
Yeah.
It kind of got like confusing. Because we always had to like erase and then rewrite and redraw whatever. But this is like a lot easier.
Yeah.
It's like you know how to work with that.
Well, there's also features on here that don't exist in the smart software.
Like, when you have like the lasso around and you can move that, that's a lot nicer.
Yeah, there's a lot. All right, guys, so here is the disk. And probably, maybe I should actually do, how do I want to do this? Maybe I'll do it the other way around. Let me flip it. So I'll just rotate it by. All right, so. Good question. What's the difference between a disk and a hoop? That's right.
Wait, so Mr. Blue, what was
That's annoying.
what was this?
That was the hoop.
The hoop.
This is the disk. So maybe I should let me make it solid. How do I do that? Maybe there's got to be a way to do this. Is there an autofill?
There's probably a fill to it.
Yeah. Whatever, it's fine. I think at this point and just. I think I made it worse. All right, so this is a disk. So now, what was the electric field do to a hoop?
Blue hoop is in a straight.
That's a big electric field.
Okay, so here's x. And what I'm going to do here, stay focused, guys, stay focused, is this is going to be my r.
Okay.
Not halfway, but imagine what I did was pretty interesting here. I took my disk, which was much larger than this. If I have a piece of paper. No, I need like a large disk. Oh, here. All right, perfect. So here's your disk, right? And so now what I did was I'm looking. So let's suppose this is a solid disk. And what I'm doing is I'm saying, all right, let me take a hoop from this disk. This is solid, right? That's right. So what I'm going to do is I'm going to use the work I've already found or I've already done. Let's see. Here we go. Perfect. So what I'm going to do is an electroscope. It's an electroscope. It's your normal electroscope. All right, so there you go. So this is the hoop. This hoop is little r away from the center. It has a width of dr. So now, what do we know about the electric field that's generated from that element? It's going to be identical to the electric field associated with the hoop. So let's actually look through this. Now this is script r, that's little r, right? dr is this width. So now, what is the electric field due to the hoop? E hoop is going to be what? Go back in your notes. What? Wait, no, what? It was script r cubed, right?
Oh, I guess, yeah. You just replaced it. So. Oh, no, that was later. You supposed to keep x squared plus r squared 3.5.
Right? So this is then going to be lambda x over 4 pi epsilon 0 x squared plus r squared, right? So 3 halves?
Yeah.
I don't know. I'm asking you guys.
2 pi r on top.
2 pi r? Yeah.
No, he said it.
So it's lambda x times that quantity?
Yeah.
All right. So beautiful. Because guess what?
X is constant.
Now what do we have to integrate over? Little r, right? So in other words, E is going to be the integral of this thing from what to what?
Wait, 0.
So an E disk.
So RG.
Actually, I should probably write it like this. E disk is equal to the integral of dE hoop. which is equal to the integral of that times 2 pi r dr.
There's no integral. Does the E hoop change? It does change?
Well, it's just that what you're doing is you're constructing the disk from what? That's right, from a series of hoops that are extending from...
Does E hoop just come out?
No, you have to keep it in because each one of those hoops are a variable distance away from the center. So this is a clever way to do this. The non-clever way was to do it starting from scratch. Huh? No, we're not going to, no need to do this. Because the real clever way is to actually go straight to Gauss's law, which is what you're going to learn. But in order to understand why Gauss's law is just so incredibly awesome, you have to suffer a little.
Is it simpler?
Yes.
Want to understand it better?
It depends upon whether you understand it at all.
True.
No, I'm not even kidding. Like Gauss's law is one of those, it's one of those things where if you understand it, everything becomes a lot simpler. If you don't, namely the notion of flux, everything gets weird. Everything gets put into flux, for lack of a better term. So what do we get here? So now I'm going to zoom out. And so we have E disk is equal to lambda x over 4 pi epsilon 0. And then we have a 2 pi in the numerator, and then we have the integral of r dr over x squared plus r squared to the 3/2. Is there anything else I'm forgetting? I took out the 2 pi. All right. So now what? Anybody know how to integrate this off the top of their heads? U substitution is correct. So how do you do U substitution? Let U equal x squared plus r squared. You'll see. Now, du dr is equal to? Yes. What is it? Be careful. 2r. So therefore, dr is equal to du. Yeah, that's just differentiating u with respect to r.
You're basically saying the quantity.
Why wouldn't it be?
And you can just
So-
plug it back in.
X is constant, right?
Oh, that's just the derivative of U.
That's right. That's the derivative of u with respect to r. And so what do we have here?
So we have
The integral of r dr. So we have r, and dr is du over 2r times 1 over u to the 3/2. And so what happens? This becomes the integral 1/2 times the integral of u to the negative 3/2 du. And remember, we have all that stuff on the outside. What was that stuff on the outside? Lambda x times 2 pi over 4 pi epsilon naught. And then was that it? Okay. So what is the integral of u to the negative 3/2?
it's n plus 1 over n plus 1 over.
That's right. So you end up with boom, boom. You cancel those out. You get lambda x. I'll even cancel out the pi's. And then you get 4 epsilon 0. And then you get u to the negative 1/2 divided by negative 1/2.
So minus 2 du.
That's right. That is the power rule.
Oh.
Power rule.
Oh, I get that. I learned that.
Okay.
Yesterday.
No, you learn the power rule for differentiation. This is the power rule for integration.
Oh, we didn't roll
Just
today.
adding.
Oh, you didn't enroll today?
Well, we're doing like crash course on it, not like full on like. But we
Are
want
you
the
in
power.
BC?
No, AB.
You're in Miss Travis Club
Yeah.
with like 7 kids.
Yeah, 10 of us.
That's awesome.
It's a great class. I love it.
We had like 30 kids last year.
That's awesome.
There's some I'm interested in doing the whole time.
The thing is, he had to split it into 2 because of this class.
Definitely appreciate limits. It's important.
It's like 100 easy ones and then like 3 hard ones. It's
But
just
the
not-
only reason they split it into 2 is because.
So what do we end up with?
So -2.
So -2 lambda x. Oh, guys, I should probably do something going way back. See where all those lambdas are? Replace it with a sigma.
Why?
It's
Because
not linear charge.
it's a surface charge. That's right.
Ah, not a linear charge.
So sigma, sigma,
Sigma was not being first.
sigma. That's sigma. Because it's a disk, it's a surface.
Okay.
So sigma and sigma. There you go.
Even in the final answer, right? -2.
Even in the final answer, yeah, it's all going to be in terms of sigma.
So what is the final?
We're almost there.
Okay.
All right, so now, therefore we get -2 sigma x, right? And then we have a 4 epsilon naught in the bottom, and then a u to the 1/2. But u, so let's see what this is. This is equal to -2 sigma x, 4 epsilon 0. What is u? X squared plus r squared. And now, what are we going to be integrating from? Let's see if this is right.
Should we take out the 2, divide like top and bottom?
Isn't it little or?
Yeah, it's little r.
Like, what are you integrating for?
So 0 to big R. Let's see if this is right. Something's off here. Something is off. Something's off, guys. Something is off. Where are you? All right. All right, what is going on here? 2 pi r. And you sure that's right from the hoop?
Well, you told yeah, that's what, unless we did the hoop wrong.
No, the hoop's right.
I'm pretty sure.
Does everybody see how I know there's an error?
Okay, can you go back down?
I don't know.
Someone tell me what the error is. Even simpler than that. What is? That's right, because it's negative. That's right. I know something's off here because that's a negative value. So,
Well, how do you get the negative in the front and the negative in the front?
They're from innovation. But therefore,
but let's not, you know what? No. Let's actually, let's do it. I don't think it's wrong. Let's actually continue. So this is equal to negative sigma x over 2 epsilon 0, right? And then you're going to have a 1 over the square root of x squared plus big R squared minus what? 1 over x squared. 1 over the square root of x squared. That's right. And so this is going to be, I can take a negative out, and this becomes sigma x over 2 epsilon 0, 1 over x minus, and let's take a look. I factor out -1, and just flip the...
sorry. That's a lot.
All right, so now the question is, does this give me a positive electric field for all values? And the answer is yes, because this number is always going to be greater than that number.
Oh, so, okay.
So 1 over that is always going to be less than that. But notice I stopped. And this is what you guys have to do. No, I didn't lose my negative. I factor out -1 and switch them. So it's something to keep in mind. Like when you're going through the process of integration, because you're going to get caught up in sign errors. The way to catch sign errors is to keep track of them systematically, stop yourself, check for reasonability, then continue going. So, what is this? Correct. So let's look at limiting cases. First limiting case is where x is much greater than r. So if x is much, much greater than r, what do we get?
That's going to be 1 over x minus 1 over, basically 1 over x minus 1 over x.
So we got a problem. This is what we're actually going to need that formula for, the linear approximation. So let's actually go for the other case where x is... Right? I knew there was a reason why I introduced it, and it's for this. So for x much, much less than r, what do we get? It's equal to sigma x over 2 epsilon 0. Right? And what I'm going to do is going to be a 1 over x minus, so x much, much less than r, factor out 1 over r. And what do I have? Square root of 1 plus x over r squared. What happens? So then we end up with...
Wouldn't you end up with square root of 1, so you say 1 over
No, we're going to have to use linear approximations throughout. It is dirty. So actually, you know what? No, watch this. Watch this instead. This is what I'm going to do. Erase this. I'm going to distribute that x out. In other words, your E of x is going to be sigma over 2 epsilon 0, and then you have x over x, which is 1 minus x over the square root of x squared plus r squared. Right? So now we look at EX for x much, much less than r. What happens? You factor out that r, you get a 1 minus x over r square root. What's inside the square root? Right? Notice, what does this thing approach? 0. Why? Because that is 0, so that becomes 1, and x over r is approaching 0. So notice EX approaches what? Sigma over 2 epsilon 0, which is? What is that called? Starts with C. Constant.
We just said it.
Yeah, but we just proved it. There's a difference between saying something and proving it. We just proved it.
Proves the whole
That for a surface, right? If I get really close up on this surface and there's an electric field from the surface, the electric field from it's going to be constant. Meaning it's going to be constant, uniform, coming out of it. So when we get back, I'll do the other example. And then you guys,
So then what about if you're really far away?
really far away, that's the other one I'm going to do. Because how do you expect this to behave when you're really far away? Point forward charge. And if you want, you guys could actually try to show that at home. Try it out. It's not hard. You just have to use the linear approximation. So what's up?